There's a lot of talk today about artificial intelligence, but the concept of AI is actually one that is very old. In fact, if you were to look at the history of AI and the first sort of appearances of what this looks like comes thousands of years ago with the story of Jason and the Argonauts, where Jason had to travel to an island to retrieve the golden fleece to become king. And to do that, he first had to battle it out with somebody known as Talus. And Talus was, of course, the bronze man, a non human creature that was created by apparently the gods. And this was the first representation of what AI looks like. And we see this throughout history. In Judaism, we see the story of Golem. And in fact, Chinese, Greek, and Indian philosophers spent a lot of time trying to decipher if it was possible to templatize the human thinking. And today, fast forward thousands of years, we hear about things like Siri and Alexa, and AI appears to be everywhere all around us, almost like air. In fact, it was Pamela McCartney who said that AI is essentially our desire, our wish to force the gods to create something that is more powerful than us. And the big question that we were starting to ask ourselves is what happens when that desire, when that wish actually comes true, when our ability to force the gods actually. And of course, as they say, got to be careful what you wish. So AI began not with Alan Turing or McCarthy, but with the ancient wish to forge the gods. Of course, from Pamela McCartney, Machines Who Think. That visualization there is just 3% of the neurons in our brain of the thalamocortical system. That magical thing between our ears that allows us to see and hear and think and reason and hope and dream and fear our eventual mortality. All of that is the thing we wish to understand. That's the dream of artificial intelligence and recreate versions of it, echoes of it in engineering of our intelligent systems. That's the dream. We should never forget in the details of the talk. That's sort of the reason why this is exciting, this mystery. That's our mind. The modern human brain, the modern human, as we know them today, it's just about 300,000 years ago. And the industrial revolution is about 300 years ago, because that's 0.1% of the developments since the early modern human being is when we have seen a lot of machinery. The machine was born not in stories, but in actuality, is the machine was engineered since the industrial revolution and the steam engine and the mechanized factory system and the machining tools. That's just 0.1% in the history, and that's 300 years. Now we zoom in to the 60, 70 years since the founder, the father, arguably, of artificial intelligence, Alan Turing, and the dreams that there's always been the dance and artificial intelligence between the dreams and the mathematical foundations. And when the dreams meet the engineering, the practice, the reality. So Alan Turing has spoken many times that by the year 2000 that he would be sure that the Turing test, natural language, would be passed. It seems probably he said that once the machine thinking method has started, it would not take long to outstrip our feeble powers. It would be able to converse with each other to sharpen their wits some stage. Therefore, we should have to expect the machines to take control. So that's the dream. Both the father of the mathematical foundation of artificial intelligence and the father of dreams in artificial intelligence. And that dream, again, in the early days was taking reality. The practice met with the perceptron, often thought of as a single layer neural network. But actually, what's not as much known as Frank Rosenblatt, who was also a developer of the multi-layered perceptron. And that history is zooming through has amazed our civilization. To me, one of the most inspiring things, and this is in the world of games, first with the great Gary Kasparov losing to IBM Deep Blue in 1997, then Lee Sedol losing to AlphaGo in 2016, seminal moments. And captivating the world through the engineering of actual real world systems, robots on four wheels from Waymo to Tesla to all of the autonomous vehicles companies working in the space, robots on two legs captivating the world of what actuation, what kind of manipulation can be achieved. The history of deep learning from 1943, the initial models from neuroscience, thinking about neural networks, how to model neural networks mathematically to the creation, as I said, of a single layer and multi-layer perceptron by Frank Rosenblatt in 57 and 62, to the ideas of backpropagation and accurate neural networks in the 70s and the 80s, to the convolutional neural networks, and LSTM is the bidirectional RNNs, and in the 80s and 90s to the birth of the deep learning in the on the new wave, the revolution in 2006 to the ImageNet and AlexNet, the seminal moment that captivated the possibility, the imagination of the AI community of what neural networks can do in the image and natural language space, closely following years after to the development of the popularization of GANs, generative adversarial networks. So the AlphaGo and AlphaZero in 2016 and 17. And as we'll talk about language models of transformers in 17, 18, and 19, those has been the last few years have been dominated by the ideas of deep learning in the space of natural language processing. Okay, celebrations. This year, the Turing Award was given for deep learning. This is like deep learning has grown up. We can finally start giving awards. Jan LeCun, Geoff Hinton, Yoshua Bengio received the Turing Award for the conceptual engineering breakthroughs that have made deep neural networks a critical component of computing. Perhaps the popularization in the face of skepticism, continuing, pushing, believing, and working in this field, and popularizing it through in the face of that skepticism. That's the part of the reasons these three folks have received the award. What is deep learning? It is a way to extract useful patterns from data in an automated way with as little human effort involved as possible, hence to automate it. How the fundamental aspect that we will talk about a lot is the optimization of neural networks. The practical nature that we will provide the code and so on is that there are libraries that make it accessible and easy to do some of the most powerful things in deep learning using Python, TensorFlow, and PyTorch. The hard part always with the machine learning, artificial intelligence in general, is asking good questions and getting good data. A lot of times the exciting aspects of what's the news covers and a lot of the exciting aspects of what is published and that the prestigious conferences in an archive in a blog post is the methodology. The hard part is applying the methodology to solve real world problems, to solve fascinating, interesting problems, and that requires data. That requires asking the right questions of that data, organizing that data, and labeling, selecting aspects of that data that can reveal the answers to the questions you ask. So, why has this breakthrough over the past decade of the application of neural networks, the ideas in neural networks? What has happened? What has changed? They have been around since 1940s. Ideas were percolating even before. The digitization of information data, the ability to access data easily in a distributed fashion across the world, all kinds of problems have now a digital form. They can be accessed by learning algorithms. Hardware, compute, both the Moore's law of CPU and GPU and the ASICs, Google's TPU systems, hardware that enables the efficient, effective, large-scale execution of these algorithms. Community, people here, people all over the world are being able to work together to talk to each other to feed the fire of excitement behind machine learning, GitHub and beyond. The tooling, TensorFlow, PyTorch, and everything in between that enables a person with an idea to reach a solution in less and less and less time. Higher and higher levels of abstraction empower people to solve problems in less and less time with less and less knowledge, with the idea and the data become the central point, not the effort that takes you from an idea to the solution. And there has been a lot of exciting progress, some of which we will talk about, from face recognition to the general problem of scene understanding, image classification, the speech, text, natural language processing, transcription, translation in medical applications and medical diagnosis, And cars being able to solve many aspects of perception in autonomous vehicles with drivable area, lane detection, object detection, digital assistance, ones on your phone and beyond the ones in your home, ads, recommender systems from Netflix to search to social, Facebook, and of course, deep reinforcement learning successes in the playing of games, from phone board games to StarCraft and Dota. Okay, so first the practical, the deep learning and deep reinforcement learning frameworks. This has really been a year where the frameworks have really matured and converged to popular deep learning frameworks that people have used as TensorFlow and PyTorch. TensorFlow 2.0 and PyTorch 1.3 is the most recent version. And they've converged towards each other, taking the best features or moving the weaknesses from each other. So that competition has been very fruitful in some sense for the development of the community. So on the TensorFlow side, eager execution, so imperative programming, the kind of how you would program in Python has become the default, has been first integrated, made easy to use, and become the default. And on the PyTorch side, TorchScript allows for now for graph representation. So do what you used to be able to do and what used to be the default mode of operation in TensorFlow, allow you to have this intermediate representation that's in graph form. On the TensorFlow side, just the deep Keras integration and promotion as the primary citizen, the default citizen of the API, of the way that you would drag TensorFlow, allowing complete beginners, just to anybody outside of machine learning to use TensorFlow with just few lines of code to train and do inferencing with the model. So that's really exciting. They cleaned up the API, the documentation, and so on. And of course, maturing the JavaScript and the browser implementation. TensorFlow Lite being able to run TensorFlow on phones, mobile, and serving. Apparently, this is something industry cares a lot about. Of course, is being able to efficiently use models in the cloud and PyTorch catching up with TPU support and the experimental versions of PyTorch mobile. So being able to ride a smartphone on that side. This tends exciting competition. And there is one more thing. You had to say goodbye to our favorite Python 2. This is a year that support finally, and the January 1st, 2020 support for Python 2 and TensorFlows and PyTorch support for Python 2 is ended. So let's then, from the big picture, taking to the smallest. Everything should be made as simple as possible. So let's start simple with a little piece of code before we jump into the details and a big run through everything that is possible in deep learning. At the very basic level, with just a few lines of code, really six here, six little pieces of code, you can train a neural network that understand what's going on in an image, that the classic that I'll always love, MNIST data set, the handwritten digits, where the input to a neural network or machine learning system is a picture of a handwritten digit, and the output is the number that's in that digit. It's as simple as in the first step, import a library, TensorFlow. Second step, import the data set, MNIST. Third step, like Lego bricks, stack on top of each other the neural network layer by layer with the hidden layer and input layer and output layer. Step 4, train the model as simple as a single line model fit. Evaluate the model in step 5 on the testing data set. And that's it. In step 6, you are ready to deploy. You are ready to predict what's in the image. It's simple as that. So deep learning at the core is the ability to form higher and higher level of abstractions of representations in data and draw patterns, higher and higher levels of understanding of patterns. And those representations are extremely important and effective for being able to interpret data. Under certain representations, data is trivial to understand: cat versus dog, blue dot versus green triangle. Under others, it's much more difficult. In this task, drawing a line under polar coordinates is trivial. Under Cartesian coordinates, it is very difficult, well, impossible to do accurately. And that's a trivial example of representation. So our task with deep learning, with the machine learning in general, is forming representations that map the topology this the whatever the topology, the rich space of the problem, that you are map it in such a way that the final representation is trivial to work with, trivial to classify, trivial to perform regression, trivial to generate new samples of that data. And that representation of higher and higher levels of representation is really the dream of artificial intelligence. That is what understanding is, making the complex simple. The models of the universe of our solar system, with the Earth at the center of it, is much more complex to perform, to do physics on than a model where the sun is at the center. Those higher and higher levels of simple representations enable us to do extremely powerful things. That's been a dream of science and the dream of artificial intelligence. And why deep learning? What is so special about deep learning in the grander world of machine learning and artificial intelligence? It's the ability to more and more remove the input of human experts, remove the human from the picture, the human costly, inefficient effort of human beings in the picture. Deep learning automates much of the extraction from the raw, gets closer and closer to the data without the need of human involvement, without the human expert ability to form representations from the raw data, as opposed to having a human being need to extract features, as was done in the 80s and 90s, in the early of to extract features with which then the machine learning algorithms can work with. The automated extraction of features enables us to work with large and larger data sets, removing the human completely, except from the supervision labeling step at the very end. It doesn't require the human expert. But at the same time, there is limits to our technologies. There is always a balance between excitement and disillusionment. The Gartner hype cycle, as much as we don't like to think about it, applies to almost every single technology. Of course, the magnitude of the peaks and the troughs is different. But I would say we are at the peak of inflated expectation with deep learning. And that's something we have to think about as we talk about some of the ideas and the exciting possibilities of the future.